Anything more? Yes. The LOG or the LN? So the LOG is right there. There's not another base. The only way you can do it is a common log and an actual log. That's all you can do. So if you wanted to do a log base something else, you have to use your change of base formula. Remember that one? So remember we said we could change log base B of any other log that we wanted to. That's interesting. There we go. We're going to change it to the log base, any other one we want to do. So if you wanted to type in there we go. If you wanted to type in a different log, like if you wanted to do log base 7 of 24, you can do log of 24 over a log of 7 like that.
And then I can do the same thing with the log 7 24 minus log 7 56. Like how I put that in.
You just type it in. Just type it in just like that. So you can type it in as. So if you wanted to do it this way and wanted to figure out how to type that in, you could do just log of 24 like that, and then divided by that. If you needed a numeric approximation for it, that's how you would do it. Yep. Other questions? All right, so last time we were talking about solving exponential equations. Today we're going to talk about solving logarithmic equations, and then we'll get into starting some models, and we'll finish up models on Friday, and then your exam will be on Monday. Reviews are already posted on Moodle, so you have access to those already. In any event, so let's start these. So the first batch that we have of logarithmic equations simply just have a logarithm on one side of the equation. A single logarithm on one side of the equation. These we can just rewrite using our equivalent exponential form. So remember, there's a way we can rewrite this so that we can get rid of the log and write it in the equivalent exponential form. So this is log base 27 of x is equal to negative 4/3. If you want to write this as the equivalent exponential form, what do we use for the base of the exponential? It says log base 27, what are we going to use for the base of the exponential? The 27, good. Okay. Remember, the base of the logarithm is the same as the base of the equivalent exponential. What's going to go in the exponent? It's the negative 4/3. Because remember, logarithms and exponentials are inverses of each other, right? The input of the log is the output for the exponential. The output for the log is the input for the exponential. The negative 4/3 will be your exponent, and that'll be equal to the x. Good. Yeah, that's the output. Remember, they're inverses of each other, so you're flip-flopping where the inputs and outputs goes. The other way to think about it again is just when it boils down to it, logarithms are what? Exponents, right? So the answer for a logarithm is an exponent to something. It's the exponent on the base. So this one's already solved, but we should be able to simplify the left-hand side. What does the negative tell you to do for an exponent? Flip it. What does the number in the denominator tell you to do here, the 3? When you have a fractional exponent, what does the denominator tell you to do? Divide. It's cube root, right? Remember in a fractional exponent, the denominator is the root you take, right? So this says it says flip it upside down, take the cube root and raise it to the 4th power, right? Well, what is the cube root of 27? 3. And so you flip it over, you get 1/3 to the 4th power. This ends up being 1 over 81. So again, this is 1 over the cube root of 27, which is 3, to the 4th power. 3 to the 4th power is 81. All right, how would we rewrite the next one? Yes? If you can do the exact value, I want the exact value. Yeah. Well, how would we rewrite the second one here? Okay. Good. Good. That's exactly right. So the base is 5, the exponent's the -1, the output's the 25 with the x minus 3. Now this looks like an equation we just solved last time, doesn't it? We have an exponential equation. Our first try should be, can we rewrite both sides using the same base? Yeah, what base can we use? 5, because you can rewrite 25 as 5 squared, yep. And now on the right-hand side, what do you do with the exponents? You multiply them. So what do you get when you multiply those two exponents together? 2x minus 6, good. And now that we have the same base on both sides, what can we do? Good, man, good. If the so if the exponential functions are the same, then the exponents must have been the same, right? This is that one-to-one property of exponential functions. These are pardon me, outputs of the same exponential function that are equal. Well, since it's 1-to-1, that means we had to have the inputs being exactly the same. And now we should be able to solve this, add your 6, and divide your 2. That one okay? Let's do this last one here, or this next one here, and then I'll leave the other ones for practice because they'll be similar. Pardon me. This one says log of x squared plus 19 equals 2. Now notice there's no base on it, but it says log, so what do we assume is the base? Base 10. So how can we rewrite that? Good. Yep, 10 squared equals x squared plus 19. So 10 squared is 100. What do you want to do to solve that one? Say it again. No, take the 19 to the other side. X squared equals 81. Square root, so we'll get x equals 9 or -9, right? Yeah, exactly. Good. Remember, when you do the square root of both sides of an equation, you always get plus or minus. Alternatively, you could have subtracted your 100 to the other side and factored, because you would have the difference of two squares. You could have factored at that point to get the same answer. Questions on any of those? These look like ones we've already done, right? Practice rewriting logs as exponentials, right? All we're doing in this case is just converting it to another type of equation that we've already solved. So like I said, I'll leave the next ones for practice for you. I can also post answers to them on Moodle if you want to check your answers. What's up? Yeah, I can do that. Absolutely. All right. So let's look at solving logarithmic equations with the laws of logarithms here. So what this means is that we're going to use our properties, our three properties for logs, to combine either one or both sides into a single log. Okay? We're going to do all those combining things. So just to remind, if you have the log of a product, how can you rewrite that? The way I remember it is, what are logarithms again, essentially? Exponents. What do you do with exponents when you multiply? You do what with the exponents? Add them, right? So this is log base b of x plus log base b of y. Right? When you multiply, you add the exponents. Okay. So what do you do when you divide? Subtract. Good. And if you've got a power on the inside, what can you do with the power? Bring it down, right? Now, we also worked on combining, so we can also go with the right-hand side and go to the left, right? We can always put things back together. It's really, that's what the property we're going to use here is putting things back together so that we can write, again, one or both sides of an equation with a single logarithm. Okay? So let's look at this example. I've got the sum of two logarithms, right? We got log base 4 of x minus 3 plus log base 4 of 2 equals 3. How can you rewrite the left-hand side as a single logarithm?
Log base 4 x minus log base 4 3.
So I can't break it up over the minus, right? But I've got a plus sign here. So I'm going to combine those two logs together. I add my logs. What do I do with the insides? Multiply them. So how are we going to rewrite that left-hand side? What is it? Yes, it's 2x minus 6. Good. And we can multiply the two together, right? I've got x minus 3 times 2. Right? So we're going to multiply the two things together. So we just get 2x minus 6 on the inside. And we're still equal to 3. Now this should look like what we were just doing a minute ago. Doesn't it? Isn't that exactly what the problems on the previous page we were just doing? How can we rewrite this as an equivalent exponential form? Good. Yeah, the 4 to the third equals 2x minus 6. That's exactly right. 4 cubed is 64. Add your 6. So we get 70 equals 2x, and so divide by 2 and you get 35. Now, one thing that you should get in a habit of doing, and we'll see a couple of examples of this in a minute, is make sure that whatever solutions you're getting actually satisfy the equation. And in particular, make sure the answers you get, you're allowed to plug back into the original. What kind of numbers can we not plug into a log function? 0 and what else can't we plug in? Anything negative, right? Yeah, you can only take logs of positive numbers, right? Okay. So make sure that you can put your 35 back inside there. Is the important part. We'll see one thing, an example where we won't be able to do that. Okay. Let's do the next one here. Again, the idea for this one is to combine the left-hand side into a single logarithm. In order to get the left-hand side of the single logarithm, what do I need to do first? There's something different about this first step than the previous first step. We got a 2 out in front. Good. Exactly, right? Got a 2 out in front, don't we? So what do I need to do with that 2 out in front first? Make it an exponent. That's exactly right. Make it the exponent. So we'll have log base 3 of 6x minus log base 3 of 6x, the whole thing squared, equals 3. Remember, when I bring that exponent up to the top, it's on the entire inside now. So the 6x will still be in parentheses there. Okay. Now I've got the difference of 2 logs. How can we rewrite that? Division. Good. So we have log base 3 of. Good. Any simplifying you can do on the inside? We got a 6x on top and a 6x squared on bottom. Any cleaning up you can do there? This is 1 over 6x, right? And cancel. Now does this look like, again, ones that we've already done? How can I rewrite that equation? Good. So 3 cubed is, 27. Multiply the 6x over. 6 times 27 is what? 162? And then divide the 162. So again, the idea with these is to make a single log on that one side and then just rewrite it in its equivalent exponential form like we done. And once we've got it in that single log, write it in its equivalent exponential form like we did before. Sorry about stumbling over the words there. All right. Work on the next one for a minute and then we'll chat about it. Ready to talk about it? What'd you do first? Multiplied them. Good. So you have log of x minus 24 times x plus 24 equals 2. Yeah. What'd you do next?
Just distributed x squared minus 576.
Okay. Good. Yep. Go ahead and multiply it out. That's fine. Yep. How about next?
Take the base to the 2.
And your base is 10. Good. And then equals x squared minus 576. So far, so good? Yeah. What'd you do next? Say it again.
Well, just square the 10.
So, square the 10. That's what you said. I'm sorry. I just didn't hear what you said. Okay. And then, okay. Take the square root. You get plus or minus 26. Is that what everybody got? We're not done. This is what I mentioned before, okay? So, when you do these log equations, especially when you're combining things, you might get what are referred to as extraneous solutions. The reason why is, what was our first step again? We combined them into a single log through multiplication, correct? Okay. Now remember, if I multiply a negative times a negative, what do you end up with? Positive, right? So it's entirely possible that you can put something in here that makes this negative and that negative. We know that negatives are bad inside the log, but when you multiply them together, the negatives went away, right? However, the original problem, were they together? No. Okay. So do either of these solutions down here make the inside of the original log function negative? Either of the original log functions negative. Does one or both of the solutions make the original negative? Just the negative 26, right? Okay, so we cannot use the negative 26. We only get the positive 26. Negative 26 makes the original equation undefined. Well, I'll say the original expressions undefined. So that's an important last step anytime that you're solving these log equations, is that you need to make sure that the answers you're getting make sense. Okay. So you throw out the negative in this case because it makes both of those pieces negative. That's okay? Yes?
Does it just have to make one negative?
It just has to make one of them negative, yep. If any of the expressions you have that makes it negative, then you have to throw it out. Negative on the inside of a log. Yep. All right. I'll leave that last one there for practice. Let's look at the first one on the next page here, because it's a little bit different than what we've been doing, right? The ones that we've been doing so far, we've had only logs on one side of the equation, right? This one has logs on both sides of the equation, but we're going to start this off in the same fashion. We're just going to do the same fashion on both sides of the equation. We're going to get both sides just as a single log. So our first step here is going to be what? To get a single log on the left-hand side. What are you going to do? Yes, yeah, I'll do the multiplication. Yep, you're right. So this would be log of x plus 1 times x minus 2 equals log of x plus 6. Right? That's the same first step we've done in all of them, isn't it? Combine those things together. Now, earlier we mentioned that when we were doing exponential equations, if you can get exponential equations with the same base, on both sides, then to solve the equation, you could just set the exponents equal to each other. And we're using that one-to-one property of exponential functions to do that. Well, remember, logarithms are the inverse of exponentials, right? Well, if the exponential functions are one-to-one, so are the logs. So now I've got the log with the same base on both sides. So these are both outputs of the same log function, and we say they're equal. Well, again, if the outputs are the same, the inputs have to be the same. So just like what we were doing for exponentials, if you have the same logarithm on both sides, you can just equate the insides. And again, that's using the one-to-one property. They have to be the same base. They will always be the same base, but for the problem you're doing. But they have to be the same base, but it's the same idea. You had the same output, so you must have the same inputs. And now to solve this, like Kyle said, we're going to want to multiply that thing out. What do you get when you multiply out the left-hand side? Good. And now this one, we're going to have to use factoring to solve it, yes? So move everything over to one side. So subtract your x and your 6. So you should get x squared minus 2x minus 8. How does that factor? Good. Yeah, x minus 4 and x plus 2. So what are your two answers in this case? 4 and negative 2. And then just like the previous problem, you need to check. Go back to the original equation. Can I plug both of those in the original? No. Yeah, I can't plug in the negative 2, right? The negative 2 makes all of them. Well, I guess the 2 on the left-hand side negative, right? So I have to throw out this one, and so our solution is just equals 4. X equal to 4. Do the next one for a minute, and then we'll chat about it. Yes. Yes. Oh, sorry. There you go. Ready to chat about it? What'd you do first? Multiply, good. What everybody got for the first step? Good. Now that we have a single log on both sides with the same base, what can we do next? Yeah, just equate the insides, right? Basically drop the logs off of there. What next? And you get good. And next we good. Go over the 1 minus 2x, so you get what? X squared minus 16. And either you can move the 16 back over and take the square root or factor it either way. Bless you. Either way you do it, what answers do you get? Yeah, plus or minus 4. Yep. Yeah, so does one of them not work? The negative 4 doesn't work, right? So we just get the 4. And the negative 4 doesn't work because it makes those two negative on the inside. Everybody got it? All right, I'll leave the last couple there for practice. Notice that your first step is going to be doing what, though, in each of them, rather than multiplication? It'd be division, right? Because you got a minus sign in between them. If you'd rather just do it as multiplication instead, you could always move the one that's being subtracted to the left and move to the right, and then you've got multiplication on the right, if you don't want to worry about fractions. Like I said, I'll get answers to all of these posted on Moodle, so you can see them if you'd like. We've done several of them. Yes. Yeah, it'll always, yeah. If you got one that's a minus, move it to the other side and make it a plus, yeah, you can absolutely do that. Yep. It'll, yeah, always give you the same answers. Yep. All right. I think I forgot to add the. Give me just a sec here because I think I forgot to add in my. What did I forgot to add a page. There we go. Add a page. Print out. I forgot to put this in before class. Out of sorts today. For heaven's sake, why are you not doing what I want you to do? There we go. Sorry about that. I forgot to take care of that before class. All right. Anyway, so in this particular section, we're going to talk about modeling with exponential functions. Exponential functions pop up all over the place when you're trying to model different scenarios that involve things getting bigger, growing, or getting smaller, decaying, call that the exponential decay, if it's dependent on how many things are present at a given time. What I mean by that is, if you've got bacteria, for example, it'll get bigger faster once you have more and more bacteria, because they just double, right? One bacteria splits into 2 splits into 4 splits into 8, right? So it gets bigger faster. As you go the number of bacteria gets bigger faster. But it pops up in other applications as well. For example, if you've got money that's in a savings account or whatever account, the more money you have in there, the more interest it grows. And if you leave the money in there, then you get interest that's compounded on top of the interest. It's compounded on top of the interest. And so it gets bigger faster the longer the money sits in there. So exponential functions pop up all over the time. Some of the problems, they just give you the exponential functions, or some form of an exponential function and asks you to do different things with it. So we'll see. Sometimes you'll be asked to find an exponential function. We'll do both types of those problems and answer different questions about them. So anyway, this one is modeling a species of alligator. You've got T representing the number of years. The population of the alligators after so many years is given by that 247 times 3 to the T over 3 power, where, again, T is how many years after the alligators were introduced. I know the first problem says, what's the tripling time? I'll mention that. I'll talk about that here in a second. But let me ask a different question to start with. Pardon me. What is it? The problem stem is set up as they've introduced alligators into a swamp, and then they're going to see how their population grows over time. Well, how many alligators did they introduce? It's a good question, right? How many alligators did they drop into the swamp right when it started? Well, notice that it says the population is at a time t, where t is the number of years after they were introduced. Well, if you want to know the initial number of alligators, what would you plug in for t? 0, yeah. Because that would be the time. The time 0 is when they were introduced, right? So in this case, if you calculate p of 0, this is the initial amount of alligators. In this context, it's alligators, but in any exponential growth or decay problem, if it asks for the initial amount, it's the amount at time 0. Okay? That's just general rule. If it asks for the amount, the initial amount, it's the amount at time 0. What is it going to be in this case? Well, that's 247 times 3 to the 0 over 3 power. Let's try to break it. 0 over 3 is 0. 3 to the 0 power is 1. So this simplifies to what? 247. Good. All right. So this particular, in this particular stem of this problem, the initial amount of alligators was 247. This will actually help us with the next question. It asks, what's the tripling time? The tripling time or the doubling time or whatever is just the time it takes for the population to, in this case, triple. Okay? 3 times as big. Okay? So if we want to know what the tripling time is, we want to solve an equation. I'll just write it out in words. We want to solve P of t equals 3 times the initial amount. Oops. We want to solve that for t. So we solve for t because it wants time. We do 3 times the initial amount because it's tripling time. If it were said doubling time, you would do 2 times, yeah. Okay, good. So we already said that the initial amount was 247. So basically we want to solve the equation 247 3 to the t over 3 equals 3 times 247. When is the function equal to 3 times the initial amount? That's the equation we're solving. You could multiply the right-hand side, but that's unnecessary. If I want to solve the equation, what thing do you think you want to try that again? If I want to solve this equation, what do you think you want to do first? If I have a log, I would bring it and put it down. I want to do what with this coefficient, do you think? I'm trying to get this t by itself, right? Yeah, divide it to the other side. If I divide the 247 to the other side, what's it going to do to the 247 on the right-hand side? Cancel it out. We'll get t to the 3 to the t over 3 equals 3. What do you do next? Let me help a little bit. Maybe what if I did that exponent as a 1? What would you do next? Yeah, so the exponents equal to each other, right? I have two exponential functions on the sides of the equation, right? We've got 3 to the t over 3 on one side and 3 to the first on the other side, right? So we've already done that kind of problem. We set the exponents equal to each other and then multiply by 3. And you'll get t equals 3, and the time is measured here in years. Does that make sense? All right. How do we attack the next one? It says, how long will it take for the population to reach 6,669 alligators? What would you do? Yes. Good. And solve it in the same way we just did a second ago, right? Solve it just like we did the previous one. What would you do first? Divide the 247. This one I would simplify. What do you get when you take 6669 and divide it by 247? What do you get, 27? Good. What kind of equation do we have now? Does this look like a familiar equation? What type of equation that we've solved? Yeah, it's an exponential one, right? What do you want to do in this case? Good, make the bases the same. Yeah, exactly. How can you rewrite 27 as a power of 3? 3 cubed. And now what do we do? Good. Set the exponents equal to each other. And multiply both sides by 3. And again, we're doing the time. And they told us in the problem the time is in years for this one. Or 3 times 3 is not 27. 9. Sorry. I told you, I'm out of sorts this morning. I did 3 cubed instead of 3 times 3. That okay? All right. Let's look at the next one. And then we'll do more of these on Friday. So it says, we start out with a population of 396 bacteria. Pardon me. It observes the change in population and notices that the population triples every 27 minutes. So it asks us first to find an equation. So when we're doing this, we're going to write our function. We want to write it as what looks like an exponential function. We want to have an initial amount, like we had at the beginning, and then some base to the t. Okay. Depending on what that is. Now, it might be that that base has something with a fractional exponent. It might be an ugly or little number. But this is what we're trying to go for, okay? Trying to figure out what is the initial amount and what is the base. Just like we had the previous problem, it gave it to us, right? The previous problem, the initial amount was 247. That base would have been 3 to the 1/3 power. If you think about the t over 3 being multiplied as a t and a 1/3. All right. In this case, what are we going to use for the initial amount? What are you told? 396, right? So we already know that we have 396 times some exponential function. We got to figure out what this value, this a value is. Okay. That's what the other piece of information is given to us for. It says the population triples every 27 minutes. Okay? So what does that mean in terms of the function? If I plug in 27, what should I get out? It says it triples every 27 minutes. So if I plug in 27, the minutes, what should I get out? Not quite 3, but the 3 is a goal. It triples. See? 3 times. Well, if it triples, okay, if you start with 10 and it triples, how many would you have? 30. Now, that wasn't a trick question, right? If it starts with 10 and it triples, you have 30. If it starts with 100 and it triples, 300. It's 3 times what you started with, right? So if we plug in 27 into this function, what do we want to come out? What? I still think 80. Well, not quite 81, because how many do we start with in this case? 396. So if it triples, how many do we want out of it? Okay, if you start with 10, tripling means you get to 30. If you start with 100, tripling means you get to 300. What are you doing with those numbers? Okay, so if it starts with 396, yeah, you want to triple 396. Exactly. Right. So if we plug in 27, if we plug in 27, we want 3 times 396. That's what it's asking us to find. Okay. When we plug in 27, we get 396. I don't know the base yet. Is 20 and 27 is, I'm not going to simplify it. I'll just leave it as 3 times 396. I need to get a by itself. What would you do first? I need to get a by itself. What would you do first? Divide by the 396. So you get a to the 27th equals 3. Yep. Now I need to undo a 27th power. Okay, well, how do you undo a square? Not a trick. If it was a squared, you would undo it by taking square root. If it was a cubed, you'd undo it by taking a cube root. So if I want to undo a 27th power, yeah, the 27th root, right? I need to do the 27th root. How do you write 27th root as a fraction? 1 over 27, right, as a fractional exponent. So I would write a equals 3 to the 1 over 27. And then you should be able to get a decimal approximation to that. But I can just leave it like that for our purposes until we need some numbers. We would have P of t equals 396 to the, or times 3 to the 1 over 27 to the t. And then what would you do with your exponents in that situation? Multiply them. And notice this looks a lot like the previous problem, doesn't it? It just has a t over 27 in the exponent instead of a t over 3. I'll put parentheses around that so we know that we're doing multiplication there. And again, you could do to the 3 to the 1 over 27 power and use the decimals, but we can just leave it like that as an exact thing. All right, we'll do more of these next time. I'll get answers posted on Moodle for that last handout so that you can see those the rest of those equations that we didn't do together. So, again, there's 2 reviews and a practice exam for Monday's exam posted on Moodle already with answers. Those are already up there. Okay. All right. Have a good one. We'll see you on Friday.